Okay, so in this video, I want to talk about the ratio test. There's a decent amount to say about the ratio test, how the ratio test can be used, what the cases where the ratio test gives no information look like, what the sort of comparison between the ratio and the root test is like, and I'll get into all of that. I think it's easier to have that conversation after stating the test and proving it. So I'm just going to start with that. So let me state the ratio test. So this is actually theorem 14.8, or yeah. So the ratio test says that, so if we have a series, so let n be a series of non-zero terms, then there are three cases, kind of like in analogy with the root test, right? So the series of an converges absolutely. Oops. If the lim sup of an plus 1 over an is less than 1, and the series an diverges if the lim sup, or sorry, not the lim sup, the lim inf of an plus 1 over an is greater than 1, and otherwise, if otherwise, sorry, this is sort of the case that deals with all other possibilities. So otherwise, and when we say otherwise, that's equivalent to saying that the lim inf is less than or equal to 1, and the lim sup is greater than or equal to 1. Right, so this is the situation where neither of the above cases applies. Then there's no information. So there are a series which satisfy this third condition here, which converge, and some series that satisfy the third condition diverge, right? So again, the way you should think about this is that these quantities here, lim sup of these ratios or lim inf of these ratios, they are kind of trying to measure the any possible exponential or sort of super exponential patterns that might occur in the terms an. So if the lim inf of these ratios is greater than 1, then it's kind of like this sequence of terms is growing exponentially, at least as fast as like whatever this number is raised to the nth power, basically, right? At least asymptotically, that's true. And then the same thing is true here. It's decaying exponentially in this case, or at least it's decaying at least as fast as an exponential sequence of terms. So by, in theory, you could sort of compare a sequence that satisfies this condition to some favorable geometric series to show that it converges. But actually, it turns out that the proof of the ratio test will be fairly simple because we've already proved the root test. And the reason for that actually has to do with theorem 12.2 that we proved earlier about sort of the relationship between these the lim sup and the lim inf of ratios versus the lim sup and the lim inf of roots, right? But so I'll get back to that in a second. Let's let's just prove the theorem, actually. Okay, so let's prove case 1 here. So say the lim sup, well, actually, let me just state this sort of the general inequality. So this is actually from theorem 12.2, which I just mentioned. So by theorem 12.2, in general, no matter what happens, right, we have, so we're saying alpha is the lim sup of an to the 1 over n. So we're actually going to prove the ratio test using the root test, basically, which tells you actually that in some sense, the root test is more powerful than the ratio test. And I'll explain what I mean by that after I prove this. But so if we call this lim sup alpha, then what we know from theorem 12.2 is that this has to be in between the lim sup and the lim inf of the ratios, right? So lim inf an plus 1 over an is less than or equal to alpha, less than or equal to the lim sup an plus 1 over an, right? So in case 1, the condition that the lim sup an plus 1 over an is less than 1 forces alpha to be less than 1, right? Because alpha is bounded above by the lim sup here. And in case 2, if the lim inf is greater than 1, that forces alpha to be greater than 1, right? Because alpha has to be at least as big as the lim inf here. So this literally, so then, you know, oops. In both of these cases, just apply the root test, right? And so like in this case, if you apply the root test, then you know that the series converges absolutely. And in this case, if you apply the root test, then the series diverges. And then of course, in the third one, you can actually look at the same two series. So if, you know, an is 1 over n, then the lim inf of the ratios equals the lim sup of the ratios. And the series diverges. But on the other hand, if an is 1 over n squared, then this is true, but the series converges. Absolutely, actually. Right, so this is what tells us that we can't have any information in this case because there are examples where it goes either way, basically, right? So, okay, yeah, a few comments about this, right? First of all, so what I was saying is that there's a sense in which the root test is more powerful, right? And that's really, that kind of comes actually from the fact that we proved in theorem 12.2, which is that basically the sequence of successive ratios of the terms of our series is always like worse behaved, or it's at least like not better behaved than the sequence of roots, right? So basically, like the behavior of this sequence can be much more dramatic and sort of chaotic and weird, and that kind of that bad behavior of the sequence can obscure like the information that would actually tell us whether the series converges or diverges, basically. So by looking at the more stable sequence of roots, we can always get any information from these from the roots that we could have gotten from the ratios. But there are a lot of situations where the ratios actually don't tell us anything and the roots actually do. So like for an example of that, so the root test is more powerful than the ratio test, okay? And one example of that would be something like, okay, so actually I was thinking and I realized that the example I kind of wanted to give here is actually something that I wanted to ask about as a lecture question. So let me pose the lecture question, and then when I solve it, you'll see an example of what I'm talking about here. So here's the lecture question. Give examples of, so firstly, a series AN where the lim inf of the ratios is strictly less than 1, strictly less than the lim sup of the ratios, but AN converges. And then another one where satisfying, oops. So if we call this sequence of inequalities star, but okay. And in fact, let's say also take all the AN to be greater than 0. So no negative terms. Not that you need to use negative terms, obviously. Okay, so yeah, think a little bit about it, write down your answer, submit it with your homework, and when you unpause, I will solve this or show you the solution. Okay, so here are the examples that I had in mind. So for the first one, you could take something like AN is like, or the sequence of AN would be something like, you know, let's say 2 2/3, 4/3, 4/9, 8/9, 8/27. So basically it alternates between multiplying by 2 to get from one term to the next and dividing by 3. So you divide by 3, multiply by 2. So here it's divide by 3, multiply by 2, divide by 3, multiply by 2, and so on, right? So asymptotically, the terms are actually like basically similar to just 2/3 to the n, right? So here the lim inf of the AN plus 1 over AN is 1/3, and the lim sup is 2, right? So clearly this is, it satisfies these inequalities, and also of course all the terms are positive. But if you look at the, if you actually, this series converges because the lim sup of AN to the 1 over n, in fact the limit of AN to the 1 over n should equal 2/3. So this is 2/3, which is less than 1. So the root test tells us that the series of AN converges. And for the second one, it's a similar thing, but just sort of flip which one you're dividing by and which one you're multiplying by, right? So say AN is like, the sequence AN would be something like, you know, 3 halves, 9 halves, 9 quarters, 27 quarters, 27 eighths, and so on, right? Then it just reverses. So here the lim inf would now be 1/2, and the lim sup would be 3. So it still satisfies all these properties, but clearly it diverges because actually the terms themselves just approach infinity. But if you look at like the root test, right, the lim sup of AN to the 1 over n is actually 3 halves in this case instead of 2/3, right, which is bigger than 1. So this one diverges, right? So in these cases are, you know, you can see examples of series where basically the ratio test gives us no information, but the root test actually gives us information that we can use, right? And that's basically always going to be like either there are only two possibilities, all right? Either the ratio test does tell you something, in which case the root test would also tell you the same thing, or the ratio test doesn't tell you anything, but the root test, oh, there's three possibilities, I guess. So the ratio test might not tell you anything, but the root test might tell you something, or both of them don't tell you anything. But it's never the case that the ratio test tells you something that you can't theoretically get from the root test instead. So that might leave you with the question, right? Why do we care about the ratio test, right? I mean, if the root test is just more powerful, then why do we even need the ratio test? Well, the answer is basically sometimes it's easier to use. E.g., for the sum of 1 over n factorial, right? The nth root of 1 over n factorial is, it can be estimated, and one can show it converges to 0, but this is difficult, right? On the other hand, here, an plus 1 over an is easy to calculate, right? Because it's literally just like 1 over n plus 1. So this is easy to understand. So literally, the ratio test is essentially a convenience. It allows us to analyze special types of series where the ratios themselves are easy to compute and easy to analyze, whereas the roots might not be that easy. So that does it for the ratio test. And I believe that is the end of the lecture. So thank you guys for watching, and I'll see you in the next one.